Welcome everyone to today's lecture. So last time we talked about indexing and we stopped at the point where we discussed multi-level indexes. So just to remind you, multi-level indexes can be used to build kind of like a tree structure on top of these single level indexes that we saw earlier on. And we just keep repeating this process of building, of adding one more layer, starting at the first level, until we reached a level such that all the index entries can fit into a single disk block. Okay, then we stop because once we only have a single disk block to read, there's no point adding any additional levels. Okay, and just to remind you, regarding this example that we saw for a two-level primary index. So this was basically just a single level primary index that we built earlier on. So you can see that for each index entry, we have a pointer that points to the corresponding block anchor. And on top of that, we added this second level. And you can see that the pointers here of the index entries in the second level, those point to the block anchors in the first level indexes. All right. Now, one important point to notice here is that each level of this index is, of course, an ordered file by itself, right? So I need to make sure that each level is ordered, otherwise I can't use this for searching. All right, so so we also talked about secondary indexes, so non-primary indexes last time, and this was an example here for a secondary index on a non-ordering key field of a file. So what that means is that this index field that we're using here is a key. So you won't see any duplicates here with the same values, but the file is not ordered according to this field. And that's why we had all these arrows here pointing any which way. And I'll come back to this in a second. So we looked at this example here for this secondary index, the one where we had a non-ordering key field. And we calculated the blocking factor last time, namely the index blocking factor, meaning how many index entries can I fit into a single disk block, and we calculated that that was 68. So I can fit 68 index entries into a disk block. And also the number of index blocks that I need to store the entire index file is 442 blocks. Okay, so that was significantly less than the amount of blocks that I need to store the data file. And now let's look at this in a multi-level index scenario. So let's assume that we have this secondary index, which is a dense index, right? Because we have one index entry for each search key value. Let's see how we can convert this to a multi-level index. So we already know that the blocking factor is 68. That was on the previous slide. Okay, so we can fit 68 index entries into each block. And we also computed the number of first level blocks, let's call them B1, to be 442, right? So this was exactly the number of index blocks that I need here if we just consider like a single level index, right? So then, of course, that's exactly the number of blocks that I have in the first level of my index. Okay, so now let's make this a multi-level index. So the number of second level blocks, B2, will now, of course, be the ceiling of the number of blocks that I had on the first level divided by my fan out. So what is my fan out? Well, it's exactly the index blocking factor, right? So sometimes you use FO for that. In other cases, you use BFRI, but it's of course the same number here. And just plugging this in, we can see that we need 7 blocks on the second level. And then we move on to the third level, right? So now we plug in the number of index blocks that we had on the second level and divide that by the fan out. And again, we take the ceiling of that. and that is 1. All right, and this is the point where we stop, because now on this third level, we can fit all the index entries into a single disk block. And so we have 3 levels in total. And to access any record, we just need to start at the root of this tree that we just built, right? We start at the third level, which is the root, and then we go down. And we need to access 1 block per level. So since we have 3 levels, so we call this T, the number of levels here, and it's 3, right? So it's basically T plus 1 gives me the number of blocks that I need to access to actually get to the data, right? So I need these 3 block accesses to go through the index levels, and then this 1 extra block access to actually read the data block. Now, a multi-level index is a form of a search tree. So you probably already noticed that, especially if you had the data structure course before. That, on the other hand, means that insertion and deletion needs some care, okay? Because each level of this index is in fact an ordered file. And so we can't just easily insert new records without shifting other things around. Now, what is done in practice is that we use a B tree or a B plus tree to avoid a performance hit when we have insertions and deletions. Okay, so mainly B plus trees are used, but we will also talk about B trees. For those who have not heard data structures, or even for those who have, let me just remind you what I mean by a tree here. Well, a tree is formed of multi-level nodes, and each node in a tree except the root has 1 parent node and of course 0 or more child nodes. So a node that does not have any child nodes is of course a leaf node, right? Those are the nodes at the bottom of the hierarchy. And if a node is not a leaf node, then it's an internal node, meaning it has at least 1 child. Now, sometimes we talk about subtrees. So the subtree of a node consists of the node and all of its descendants, right? So it's children and its children's children and so on. Now, in some cases, you may have trees where the leaf nodes are on different levels, right? Meaning the distance to the root is not the same. And in fact, we saw one such tree construction last week when we talked about dynamic hashing, right? So you might remember this tree where we used that tree to look up items in the hash table. So that was an example of an unbalanced tree. And there's a question in the chat, does the root, yeah, root is also an internal node, right? Assuming that it has at least 1 child. So for example, if you have a tree that consists just of a single node, then that's not an internal node, but then your root is also a leaf. Okay, and here's another example of an unbalanced tree. So you can see that some leaves have a different distance from the root, right? So this leaf here, C, has a distance of 1 from the root, whereas this leaf K has a distance of 1, 2, 3. Okay, so now let's look at how these B trees and B plus trees work. So as I mentioned, most multi-level indexes use B trees or B plus trees to solve the insertion and deletion problem. So we want to avoid taking a performance hit and still be able to add and remove records from our data file. So each node corresponds to a disk block when we look at a B tree or a B plus tree. All right, so that's pretty much the same like what we just saw for these multi-level indexes. And that means we're reserving space in each tree node for new index entries. Now, each tree node is kept between half full and completely full. Of course, this does not apply if the tree just consists of the root. And this means that I need to, in some cases, restructure the tree to ensure this invariant here, right? So that no node is below half full and no node overflows. Okay, so in case a node overflows because I added too many index entries to that node, then I need to split that node. And if a node underflows, meaning that it will have less than half of its load filled with index entries, then I'll need to merge it with some neighboring node. And of course, you might wonder, why do we need to, it's sort of obvious that we need to ensure this invariant here, right? So that a tree node can't be overfull, because a tree node corresponds to this block. So this limits what I can insert into a single node. But you might wonder why we also care about this other invariant here, that it shouldn't be less than half full. Well, if a node is less than half full, then that means that we're not using at least half of the space that we have reserved for this block. And that is of course a waste of space. So we don't want to have too many blocks where that is true. Otherwise, you're wasting a lot of memory. And similarly, this may also impact your performance if you allow nodes to become less than half full, because it can happen that your tree will have many levels, right? Because if you only have, for instance, one index entry in each tree node, so that would be kind of the worst case, then you might need a lot of levels to actually get to the leaves of your tree. So how do we insert and delete? Okay, there's a question in the chat. So what do I mean by reserve space? So, we want to store these things on disks, right? So, and the unit of transfer from the memory to a disk is a disk block. And each time I create a new tree node, I will need to basically use one disk block for that tree node. All right, so if I have many tree nodes that are less than half full, I need to use a lot of disk blocks that are not really used. Okay, so coming back to insertions and deletions. So if a node is not full and I want to insert the data record or an index record into that node, then that is quite efficient, right? Because I can just add that entry and I'm done. So I just need to find that corresponding node. I start at the root, I search through the tree, I find that node where I want to insert the entry, and that's it. But if a node is full, then insertion may cause a split into two nodes. Now, splitting may propagate to higher tree levels. Okay, so you got to be careful when you do that. So it's so if you have a multi-level tree, it's not just usually you're not done just by splitting two nodes. You might need to go further up the tree and see what happens. And in fact, it might propagate all the way up to the root. And in that case, if the root splits, then that adds another layer, another level on top of the root as the new root, and then you're increasing the number of levels of your tree. Now, similarly, a deletion is quite efficient if the node from which you're deleting an entry does not become less than half full, because in that case, I can just remove that entry and I'm done. But if a deletion causes a node to become less than half full, then you may need to merge with some neighboring nodes, right? And again, that's to ensure that we have this invariant that no node is below half full. And similarly to insertion, this merging might also propagate to higher levels, right? So if I merge two nodes on one level, then that might cause some problems to upper levels, because when I merge, then one of the parents of these nodes will have now less children, okay? And meaning they will have less entries, and so that might make them less than half full and so on. So up to now, the things that I described apply to both B trees and B plus trees. And the difference is that in a B tree, you have pointers to data records on all levels. Okay, so keep that in mind. Whereas in a B plus tree, we only have pointers to data records on the leaf level. So what other pointers do I have in a B plus tree? Well, the B plus tree is similar to those multi-level indexes. So the internal nodes will only have pointers to other B plus tree nodes, but not to actual data records. All right. Now, as a consequence of this, we will see that the B plus tree can actually have less levels and therefore a higher capacity for search values than the corresponding B tree. And the reason for that is quite simple, right? So since you don't have any data pointers to data records that you need to include in the internal nodes of a B plus tree, you can possibly fit in more tree pointers. All right, so now let's look at the B tree in more detail. So the B tree organizes its nodes into a tree. That won't surprise you, I guess. And why is it called B tree? Well, it's a balanced tree. So that's what the B stands for. And as I said, that means that all paths from the root to a leaf node have the same length. Now, this figure here is not exactly a B tree. It's just a generic search tree. And but it kind of conveys the idea. So what this means here is that I have 3 different key values here, 57, 81, and 95. Okay, and now I have these 4 pointers. Okay, and the first pointer points to a subtree, or rather to a node, and in the tree, and below this, like the whole subtree below this, will only have key values that are less than 57. Now, similarly, this second pointer here will point to a subtree that only has key values that are in between 57 and 81. Okay, and similarly, this pointer here will only have will point to a subtree that has key values between 81 and 95. And finally, this pointer here will point to a subtree that will only have that will only concern itself with key values that are greater than 95. So there's a question if I do the n plus 1 pointers. So what is n? So we'll look at the number of. So in this case, we're setting p is equals to 4, and when we talk about these trees, p is the order of the tree because it tells us how many key values we can have, and usually, sorry, how many pointers we have, right? And so that's usually we only look at the number of pointers that you have in a single block, but we'll come back to that. Okay, so now let's look at the specific shape of B tree nodes. So each internal node of a B tree is of the following form. So you have you start with some tree pointer. So P1 is the first tree pointer, and then you have a pair K1 and PR1. So each PR1 here is a data pointer. Okay, so that points to some actual data records. And what data records does this point to? Well, those who have a search field value of K1, right? So K1 is some search field value. Maybe it's some integer. Maybe it's 20 or something, okay? And after that, I have another tree pointer. And this is followed by another pair consisting of a search key value and a data pointer and so on. Until at the very end, I also have another tree pointer. Now, what we want here is the property that each one of these search key values here is greater than its predecessor, right? So it needs to hold that K1 is less than K2 all the way to KQ minus 1. And now we have this property for the search key field values in the subtrees that are pointed to by these tree pointers, P1, P2, and so on. namely that the search key value should lie between the keys, depending on where the location of the pointer is in this tree node. So what I mean by that is that if you look at the subtree, the one to which P1 here points, that one needs to have only search key values that are less than K1, right? So this would be the second condition here. So X less than K1 in this case. And similarly, if we look at now, let's say at P2, then that should point to a subtree such that the search key values should be in between K1 and K2. Okay, and so on. So this is exactly this works exactly the same way as I just showed you on this previous slide here, right? And similarly for the very last one, for PQ, so that will point to a subtree such that all search key field values in the subtree, so all such values X, need to be larger than this final key Q minus 1. And there's a question about this Q here, so I was going to come to that. So each node has at most P tree pointers. But so it can so in this case here, so it can have, of course, less. So we say it can have up to Q tree pointers, where Q is at most P. Okay, so we say P is the order of the tree because it gives you the maximum number of tree pointers that it can have, and also it gives you an upper bound on the maximum number of such of these pairs here that you have, the key and data pointer pairs. So you have at most P minus 1 many of them. And there's another question. This requires sorting the data in one block, right? So yeah, I mean, this order here, of course, so usually we assume that we're inserting things into a node one item at a time, right? So when we insert something new into a node, we need to insert it at in the right place. So in a sense, yes, we're sorting within one block. And now this last sentence here, down here, that one gives us the invariant that I mentioned early on. So except for the root and the leaf nodes, each node will have at least P by 2 rounded up many tree pointers. Okay, and the previous bullet point here gives us the second half of the invariant, namely that we have at most P tree pointers. All right, so yeah, so there's not really any rotation going on here. So these are not like the trees that you probably learned about in data structures. So this is a bit different, how these B trees and B plus trees work. Now, all the leaf nodes are exactly on the same level. So the tree is balanced. And all the tree pointers are, of course, null, right? So they don't point to anything else. But their data pointers are not necessarily null. So here's a concrete instance of a B tree. So up here you have the general form, right? So this is pretty much what I mentioned on the previous slide, right? So P1 is the first tree pointer, it points to some subtree, and all the search key values X in the subtree must be less than K1, which is this first search key value here in our node. And here, this is this pair K1, PR1. So PR1 is the data pointer that points to the data records that have exactly key value K1, and so on. Then we have the next tree pointer, and so on, all the way up to PQ. And down here we have a concrete instance of such a node, of such a B tree node with some concrete values. So here the order of the tree is 3, right? So we have at most 3 tree pointers. And in fact, the root here has exactly 3. Okay, and you can see here the search key values, so 5 and 8. And this pointer here will point to a subtree where you only have search key values that are less than 5. And similarly, this one here will point to a subtree where you have search key values between 5 and 8. And similarly, this one points to a subtree where you have larger search key values. And these here are the data record pointers, so we're kind of omitting them. No, so this whole rectangle here is a tree node. Okay. This whole thing here is a tree node, and similarly, this whole thing here is a tree node. This is just part of your tree node. Is that clear now? Good. All right, let's move on. So let's look at the capacity that we get for such a B tree. So let's assume that we construct a B tree on some search field, and we set the order P of the tree to be 23. Okay, so you can have at most 23 tree pointers per node. And we assume that each node is around 69% full. So this is not some number that I just came up with, but rather this, so people have done some experiments. And if you keep, let's say, doing some random insertions and deletions into a B tree, then on average, you will see that it becomes, that the nodes will be 69% full, okay? So on average, we can assume that each node will have, so if we multiply 0.69 with 23, which is the maximum number of tree pointers that each node can have, then we will assume that it has 16 tree pointers, okay? So that's our fan out. So what about the root? Well, of course, we only have one node on the root level, and we have 16 tree pointers, right? So that's our assumption here. And therefore, we have 15 key entries. So why do I have one key entry less? Well, that follows immediately from the structure here, right? So you can see that you always have one of these tree pointers more than you have these pairs of keys and data pointers. Okay, so that's why we have 15. Now on the second level, sorry, on level 1, I should say, usually this is called level 0 and this is called level 1. So how many nodes do I have? Well, I need to have 60 nodes because I have 16 tree pointers on the root level. And how many key entries do I have? Well, I have 240. Can someone tell me where I got this from, this 240? So that's the total number of key entries that I have on this level. Right, so it's 16 times 15, right? So I have 60 nodes, and each node has 15 key entries. Okay, so therefore in total on this level I have 240 key entries, and I have 256 tree pointers, right? Because each one of these 60 nodes has 16 pointers, so 16 squared is 256. On level 2, therefore we have 256 nodes, the ones that we pointed to on level 1. And again, each one of them will have 15 key entries. So 15 times 256 is 3,840, and 256 times 16 is 4,096. And then moving on to the third level, we get 4,096 nodes and 61,440 key entries, and so on. So you can see that as you go down your level, the number of key entries that you have is getting very large. So if the search field is a key field, then all the search values k that occur will be, of course, unique. And otherwise, sometimes we also want to construct indexes on non-key fields, right? We saw some examples of that last week. So you might have some repeating values. So in that case, we'll have a data pointer that will point not just like to a single record, but to a block that contains pointers to file records. So that is similar to how we handle this with the secondary indexes. Okay, and so what is the maximum? So let's say we have a tree with an order of p equals 4. So what's the maximum number of key values if we have 3 levels? And we assume that all nodes are full. So not just 69% full, but completely full. What's the number of key values that I have on the 3rd level? Or I shouldn't say 3rd level, level 2, right? Because root is level 0, then level 1, and then level 2. Well, how many do I have on the root level? How many key entries? So I have 4 tree pointers, right? So I have 3 key entries. So I have 1 node, 3 key entries, and 4 tree pointers. So that's level 0, and level 1. How many nodes do I have? Well, I have 4 nodes, right? And therefore, I will have, since my order is 4, I will have 4 times 3, which is 12 key entries and 16 tree pointers. And then on the 3rd level, level 2, I will have 16 nodes and now 48 search key values, right? Okay. All right. Now let's move on to the B+ trees. So here the difference is, as we already talked about, that data pointers are stored only at the leaf nodes of the tree. So the pointers in internal nodes are tree pointers, meaning they point to nodes that are tree nodes. And the pointers in the leaf nodes, those are the actual data pointers to the file records that we're interested in. There you go. But of course, you can find this on Zoom as all lectures are recorded. So the leaf nodes of a B+ trees, so they're usually linked together to provide an ordered access to the records. One consequence of the way we store things in a B+ tree, meaning that we don't have any data pointers in the internal nodes, is that we can pack more tree pointers into an internal node. Okay, so we will need less levels compared to a B tree. All right, so here's the formal structure of the internal nodes of a B+ tree. So each internal node will be a sequence of tree pointers and search key values. So we alternate between the two. And we have at most Q many tree pointers, where again, similarly to the B trees, Q is less or equals than P. So as I mentioned, each PI here is a tree pointer, so it points to some other node. And of course, it needs to hold that the search key values are strictly ordered. Now, then we have a very similar condition here on the search key field values in the subtrees that we point to by our tree pointers, but it's not exactly the same as for B trees. The main difference here is that we have this lesser equals for instance, when you look at the subtree that is pointed to by P2 here, so all the search key values in that subtree need to be larger than K1, but only lesser equals than K2. Okay, so I might have some data records in there that have a value of K2. And the reason for that is that we don't have any data records in such internal nodes, right? So I can't exclude this here. I can't use a strictly less here like I did for B trees. All right, and of course, these two conditions, those two capture just the polar cases of the first 3-pointer and the last 3-pointer, right? So that's very similar to B trees. So as we mentioned, each node will have at most P 3 pointers. So again, we have this invariant, and each node, except for the root and the leaf nodes, need to have at least P by 2 many 3-pointers. So this is again this not below half full invariant that we had for B trees. So what I mentioned here on this slide is only for the internal nodes. All right, so now let's look at the structure of the leaf nodes. So each leaf node will have the following form. So now you can see that we don't have any 3-pointers here. So we kind of removed those if you think back to the shape of the B tree nodes. So we only have these pairs of search key values and data pointers. So K1, then PR1 is a data pointer, and so on. So here at the end, we have P next, which just points to the next leaf node in sequence. So we just link all the leaf nodes together as an ordered sequence, just to make it more efficient to access all the search key values in order. Okay, and now we have, again, we have at most Q many such data pointers in a leaf node. And this Q now needs to be at most P leaf. And this P leaf here might be different than this P here. Okay, so we might have a different order for the internal nodes compared to the leaf nodes of a B plus tree. Again, we need this invariant here that the search key values are strictly ordered. And as I mentioned, each one of these data pointers here will point to a record whose search field value is exactly the same as the the associated search key value. And similarly as for B trees, if this is a non-key field, right? If there are multiple such records, then it will just point to a block that has multiple pointers to the actual records. So this P leaf, as I said, is the order of a leaf node, and it gives us the maximum number of such data pointers. And I also mentioned already what P next does, right? It just points to the next leaf node. And now, of course, we need to have this invariant that we have at least P leaf by 2 many such values in any leaf node. All right, and just keep in mind that the B plus tree is also balanced. All the leaf nodes are on the same level. So here is a concrete example for a B plus tree. So up here we have basically the formal definition of an internal node, right? So we have all these 3-pointers here that are interleaved by the search key values. And underneath each of these subtrees, you can see the corresponding condition that needs to hold, right? So all the search key values X in this subtree need to be less or equals than K1, and so on. Same is true for each one of these subtrees. Down here in B, we can see the structure of a leaf node, right? So we have all these data pointers, and each one of them is together with an associated search key value. And at the end, we have this pointer P next, which just points to the next leaf node in the sequence. Okay, so now let's look at an example of how we can compute the order for a B plus tree for the internal nodes and the leaf nodes. So let's assume that we have a search key field that takes 9 bytes. And let's assume that we have disk block sizes of 512 bytes. And the size of a record pointer is 7 bytes, and a block pointer will have 6 bytes. Okay, so with these measures in mind, so there's a question in the chat. So can we reduce the storage capacity? So I'm not sure what you mean by reducing the storage capacity, but maybe we can come back to that after I finish this slide. So an internal node of a B tree can have up to P tree pointers and P minus 1 search key field values, right? And of course, all of these need to fit into a single disk block because we said one node corresponds to a disk block. Okay, so this means that this inequality here needs to hold, right? So I might have P many tree pointers. So each one has 6 bytes. So I have P times capital P. And then I have P minus 1 many search key fields, right? And each one of them has V, which is 9 bytes size. All right, so adding up these two, that still needs to be less or equals than the block size. Okay, and so I can just plug this in, and this will tell me that I can choose P to be 34. Okay, so this way we could determine the order of the internal nodes. And now let's compute the order of the leaf nodes. So I'm doing a similar calculation here. So whatever P leaf needs to be, I know that I will have, one data record entry, one data pointer and one search key value associated with it. So I will have at most P leaf, many of them in my leaf node. And then at the end of the leaf node, we have this P next, right? So we have a block pointer to the next leaf, okay? And the sum of these two needs to be, again, at most the block size. And now plugging in the values for PR, V, and P, we can compute that P leaf is at most this, right? And therefore we can choose P leaf to be 31. Okay, so you can see that these two are not always the same, and it doesn't make sense to choose the same order for leaf nodes and internal nodes, because that means you would need to choose the smaller of the two and you would waste some space. Okay, so now let's look at the capacity that we get for a B plus tree. So there's a question. So how to determine? Oh, actually, I wanted to come back to the previous question before I address this question. So I'm not sure I understand your question. How can we reduce the storage capacity? What exactly do you mean by that? You mean that you can store things more efficiently? Well, compared to what? So I guess the main point, that the main advantage of B plus trees and B trees is that they reduce the search time because they work like an index. All right. But of course, if you don't care at all about performance, you can see that we're wasting some space, right? Because we need to take into account all the space used by these pointers here, by the block pointers, by the record pointers, and so on. So if I omitted all that, I could just store the file as it is, and I would use even less space. Okay. All right, and there was another question further up. Let me see. Where was that? Oh, how to determine when a block pointer and when is the block? So you mean when we're using a record pointer and when a block pointer? So there's a simple rule for that. So whenever we are pointing to data, we're using a record pointer, so we're using PR. But when we're pointing to another tree node, then we're using a block pointer because each tree node corresponds to a disk block. Okay. And so therefore this P next here is a block pointer because it points to another leaf node, which is a disk block. All right, so let's look at this example for the B plus tree capacity before the break. So again, we're assuming that each node is 69% full. So this was the same assumption that we had for B trees. And therefore, on average, each internal node will have now, so this 34 here is the order that we just computed, right? So we will have 34 times 0.69, meaning we have 23 pointers on average, and therefore 22 search key values in each internal node. And similarly for each leaf node, we have we get that if we multiply this 0.69 with the value for P leaf that we just computed, we'll get that we have 21 data record pointers on average in each leaf node. All right, and now let's look at what we get. So on the root level, we have one node and 22 key entries, right? That's what we set up here. We have 22 key entries and 23 tree pointers. So therefore, on level 1, we have 23 nodes. And now I have 506 key entries. So again, this 506 is 23 times 22, right? So that's where I got that from. So each one of these will have 22 key entries. So now in total, I have 506 key entries on level 1, and 23. Yeah, and each one of these will have 23 pointers. Okay, so 23 squared is 529. And similarly, on level 2, we have 529 pointers and 11,638 key entries and 12,167 pointers. Okay, and on level 3, we get these values here. Okay, and you can, if you compare this with the values that we get for B trees, you can see that we have a lot more nodes on the same level when we look at B plus trees. Okay, and also a lot more data record pointers. So what this tells us that is that we can store a lot more data record pointers and still keep the number of levels relatively small. All right. Yeah, there are a lot of data record pointers, that's true, but databases have sometimes millions or billions of data records. In some cases, even trillions. How do we count the data record pointers? Yeah, so we're using the fact that up here we said that each internal node will have on average 23 pointers. Okay, so we're assuming that this is true for all the internal nodes. So therefore, so the point is, let's say if I want to store 255,000 data records in my database, right? Then I construct the B tree or I construct the B plus tree. So if I construct the B tree, I will need more than 3 levels to store to access this many data record pointers. Okay, so my search time will be increased, right? Because simply because I need to access more blocks because I have more levels. So that's why in practice, most of the times we will use B plus trees. Okay, so B plus trees are more effective. All right, so then let's take a 10-minute break. So there's another question. So how did we get these data record pointers? That's your question, I guess. Yeah, okay, so someone already answered it. All right, then let's continue after the break. All right, so let's continue. And the next topic that we're going to discuss are database transactions. So let's start by defining what a transaction is, and then we'll talk about the so-called asset properties. So in most cases, the user won't directly perform database accesses. Okay, so you might remember from some of the previous lectures that we're usually dealing with a database management system, DBMS, which is a set of software that provides an environment for managing data in databases to support various applications. Okay, so instead of directly interacting with the database, what the user usually does is the user will access some application, and that application will use a software interface to communicate with the DBMS by performing transactions. Okay, so every operation that you perform on the database usually is part of some transaction. Now, more formally, what is a transaction? Well, a transaction is so you have a formal definition here. So the execution of a program or application on behalf of the user to perform a specific user function by accessing the data items that are in the DBMS. Okay, so for instance, one example is the use of an ATM or buying online tickets, right? So we all do transactions every day. So there's a question in the chat, so like Oracle. So all of these database systems have transactions built in. Okay, so you might have already encountered the commit command in SQL. So that's how we commit transactions. And in general, you can think of these transactions as being processes that are created by the DBMS and that only work in its environment. So your operating system isn't aware of these transactions. They only exist inside the DBMS. So we can think of them as being a logical unit of database processing. So as I mentioned, every command that you're executing will be part of some transaction implicitly in some cases, so you don't need to specifically mention it. And of course, a transaction needs to include at least one database access operation. So that might be some retrieval or inserting new records or deleting records, something like that. So transaction itself consists of atomic steps, and each atomic step is called an operation. Okay, so a transaction consists of some database operations, and then you also have some transaction operations. For example, commit would be a transaction operation. So we're already very familiar with database operations. So that means when we're reading or writing to or from the database. So we've seen some read operations, which are used to read a value of a data item or some group of items. So for instance, this is what the select statement does in SQL. And we've also seen some write operations, right? So sometimes we want to update some records or delete them. So we've seen the update command in SQL. And of course, you can also perform some computations in a transaction, right? So you might run some select statement and then perform some computation on the result of the select statement, and then use that computation to update some other values in some other table. And you want these things to happen atomically, meaning as one logical unit. So then you would pack them into the same transaction. So a transaction, so as I said, a transaction consists of database operations and also of transaction operations. So we have a begin operation that tells the DBMS that this is the point where transaction starts. In some cases, that is implicit. And we also have an end operation. So that is usually a commit or an abort or rollback. Okay, so in some cases, we want to discard the transactions. In that case, we need to abort it. So of course, these transaction operations are used for managing the transaction, right? So we need to know where it starts and where it finishes. And the important point is that the new values that you may compute in a transaction and try to insert into the database, those become only permanent if the transaction is committed successfully. So in particular, anything that has happened since the beginning of the transaction, if a transaction is aborted, all of these things are discarded. So there are no partial results that may show up in your database. And usually this is called atomicity, right? So a transaction is an atomic unit, so it's either all or nothing. And here's an example for a transaction. Let's call it T1. So this begin here just denotes the start of the transaction. And then we write the result of a read of some data item A into the variable capital A. And similarly, we read some item B from our database. That's what the R stands for. And we write the result into the capital B variable. And then we compute the result of A plus B and write it into variable C. And then we write to our database. So that is the capital W here with a, we write this to item C. And we write the result that is in capital C. And then at this point here, we end the transaction. So we have this end here. Okay, so this is kind of a pseudocode. Of course, this is not SQL code or anything. This is just to give you a feel what you can do in a transaction. So one important thing to keep in mind is that when we start the transactions right at the beginning here, we are guaranteed that the database is in a consistent state. And then as we start executing this transaction, the database may be temporarily in an inconsistent state. Okay, so for instance, I might transfer something from one account to another in a bank. And maybe at some point here, I have deducted some amount from the first account, and I have not yet added it to the second account. So the database is in an inconsistent state, right? Because the money that I deducted from one account is now currently vanished. And only at the end of a transaction, we're guaranteed that the database is back in a consistent state. So therefore, we want to make sure that this whole thing here, this whole transaction is considered to be an atomic unit. So here we can see two sample transactions, T1 and T2. And I'm only showing the database operations here, so I'm omitting the begin and the end. So what T1 does is it transfers n reservations from one flight whose number of reserved seats is stored in some item X. So it reads item X to another flight whose number of reserved seats is stored in item Y, right? So I'm reading X and then I'm subtracting n, a value of n from X. Okay, but this only happens in our variable X. So this is not yet updated in the database. And then I write the item X back to the database. Then I read the item Y from the database, and I add to the value that I read the value n that I subtracted from X, right? So I'm adding n reservations there to Y, and then I actually update this in the database. Okay, so here we're not really worried about how read is actually implemented. So when you have an index on top of your data file, then this might actually be quite efficient. And this transaction T2 here, we can think of it as like reserving M seats on the flight X, right? So we're reading the current value of X, and then we're adding M to that, and we're writing it back to the database. So before going into more details about how transactions are scheduled, let's first take a step back and clarify what we mean by a read or a write operation. So you might recall that I already mentioned to you that, of course, the data resides on disk, and the basic unit of transferring from the disk to the main memory is one disk block. Okay, so in general, a data item that is either read or written will be, so when we're not really specific what we mean by that. So it could be, let's say, the field of some record. It could also be the whole record itself. But the point is it has to be stored in a disk block. So now that we clarified this, let's look at what read item X actually incurs. So this requires us to find the address of the disk block that contains this item X. Okay, and once we have that address, we can copy that disk block into a buffer in the main memory. So this is where the IO processor comes in. Of course, we only do that if the disk block is not already in some main memory buffer, otherwise we don't need to bring it there. And then we search for the required value in that buffer, and we copy that the item X, the one that we want, from the buffer to the program variable named X. Okay. So you can see there's a lot of things going on, a lot of things here going on just for a simple read. Now, what about writes? So this is kind of similar. So again, we need to find the address of the disk block that contains item X. And then we need to copy that disk block into a buffer in the main memory if it's not already there. And then we need to search for the required value in that buffer. That's usually much faster than this copying step here. And then we copy item X from the program variable named X into its correct location in the buffer. Okay, so the point is we need to have this buffer here in between. We can't just like copy the whole disk block into our program variable because we want our program variable to be small, right? So we don't want each program variable to waste space by allocating the size of a disk block for that. All right, and of course, since this is a write, we need to store the updated block from the buffer back to the disk. Okay, so sometimes this is done straight away. In other cases, we might delay this to some later point in time. So here you have this interplay between your program and your program variables where we're performing our transactions and the buffer that we're using to temporarily store these disk blocks. And of course, these are written back and forth from to the actual hard disk, which is our permanent storage. Okay, so now that we understand what transactions are, let's look at the so-called ACID properties of transactions. So ACID is an acronym and it stands for atomicity, consistency, isolation, and durability. So let's look at each of these properties in turn. So basically, these properties ensure that we get a result that corresponds to what we expect when executing transactions. Okay, so these properties need to be enforced by the DBMS, or rather, more specifically, by the concurrency control and recovery methods of the DBMS. So as I mentioned, atomicity means that a transaction is an atomic unit of processing. So either all the actions in the transaction are performed or none of them. Okay, so it's all or nothing. Consistency requires that the correct execution of a transaction must take the database from one consistent state to another. And isolation means that the transaction should not make its updates visible to other transactions until it is committed. So we shouldn't have like partial results showing up. And durability means that if a transaction changes the database state and the changes are committed, meaning that transaction successfully terminates, then these changes must never be lost because of subsequent failures, right? So even if my PC crashes afterwards, that should still be there in the permanent storage. So there's a question: what if the things input already exist? In what context? So we'll see some examples for transactions. Maybe this will clear things up later. Note that durability doesn't mean that I can't delete records, right? So it just means that the state is durable. All right, so let's talk about how to improve transaction processing performance. And one key question that we need to look at in this context is what the difference between serial schedules and serializable schedules of transactions. So nowadays, most modern systems will support concurrent execution. So what we mean by that is that we have many processes that access the database concurrently at the same time. Okay, and there are mainly two types of concurrent processing that we need to distinguish. So the first one is interleaved processing. So here we're looking at concurrent execution of processes and transactions that are interleaved in a single CPU system. All right, so we have just a single processing unit, but we might have multiple transactions that are going on at the same time. But of course, only one of them will perform specific operations at any single point in time. So that's why it's interleaved and not parallel, which brings me to the next form of concurrent processing, which is parallel processing. So in that case, we're looking really at multi-core systems. So you might have multiple CPUs that are issuing multiple operations at the same time. So here in this lecture, we're just going to focus on the interleaved processing. That's complicated enough. But you can actually think of parallel processing as a special case of that. But yeah, we won't have time to go into the details for that. All right, so why do we want to have concurrency? Well, generally speaking, concurrency means that we get better performance, at least in some cases. For instance, we can have lower response times. For example, if you look at the case where one transaction needs to fetch a disk block, so it needs to read some item, and this item is on a disk block that is not yet in the main memory buffer, then that needs to be fetched from the hard disk to the main memory buffer, and that might take some time. So you don't want to wait for that to happen. There might be some other transaction that meanwhile can do some useful work. Okay, and this way, if you have interleaved processing, you can actually get some better performance than just doing everything in sequence. But if we have concurrency, the problem is that it's more difficult to maintain these ACID properties that we mentioned just before. All right, and here is a picture of the difference between interleaved and parallel execution or processing. So here on the left, we have an interleaved processing, right? So there's only a single, so time runs from left to right. And you can see that here we're running transaction A, then here we're running transaction B, then we're jumping back to A, and so on. So at any single point in time, there's only one transaction that is active. Or rather, there's one transaction issuing operations here. And here, on the other hand, we have two separate CPUs, and you can see that two transactions, C and D, are running simultaneously, and we have a true parallel execution. As I mentioned, we're going to look at the interleaved concurrency model for the rest of this lecture. All right, so let's talk about transaction schedules, and let's assume that we have n transactions, T1 to Tn. So what's a schedule? Well, a schedule S is just the total ordering of the operations in these transactions. Okay, so for each transaction Ti, the operations of Ti in S must be, of course, in the same order as they are in Ti, right? So whatever the order of operations is in Ti, I can't just change their order. But what I can do is I can interleave the operations of different transactions, right? So operations from other transactions, Tj, can be interleaved with the ones from Ti in the schedule. Maybe I first do a read for transaction T1, and the next operation would be a write for some item in T1, but maybe I first do a read of some item for transaction T2. Okay, so that's perfectly possible in a schedule. Now, if we do that, then we have a concurrent schedule. So a new transaction starts before the completion of the current transaction. On the other hand, if we don't allow that, if we want a new transaction to only start after the current transaction has completed, then we have a serial schedule. So everything happens in sequence. So let's look at an example for a serial schedule. So here we have two transactions, V and W. And this is kind of a made-up example, right? So I'm looking at basically at a bank with some accounts. And here I'm so this is the code for transaction V, right? So transaction V has only these two operations here. So I'm withdrawing from account A 100, and then I'm depositing on account B 100. That's it. Now transaction W will execute this branch total function for some branch. Okay, so this will just compute the total balance for all the accounts associated with one specific branch. So there's a question: do we need to construct serial schedule or concurrent schedule? We'll come to that later on. We'll talk much more about schedules in a second. And down here, now we can actually see a schedule. Okay, so time runs from top to bottom. So this would be the flow of time, right? So we're starting up here, and then we're jumping over here. So initially, we execute a dot withdraw 100. So we're executing this withdraw function for this account A. Okay, and if the initial value of account A was 200, then after this it's 100, and then we're depositing on account B 100. So if the initial value was 200, then it will be 300. And after this, we're executing transaction W, right? So we're done with transaction V. So this is a completely serial schedule. So I'm first completing one transaction, and only then I'm starting the next one. And here I'm getting the current balance of A. So the current balance is 100, right? Because that was the result of this transaction V. And then I'm adding to the total variable here the balance of B, and let's assume it was 200, right? So 200 plus 200 is 400. And then I'm doing the same for C, right? So I'm adding this to my total, and so on. Well, this just shows you what's left on the account. Okay. Exactly, right? So we started with 200, and then we withdrew 100, so it's 100 that is left. Okay, so this was a serial schedule. And now let's look at a different schedule and different transactions, and let's look at a concurrent schedule. All right, so here we have two transactions, T and U. They're doing some strange things, so don't worry what they're really doing. That's less important. What's more important is that we can construct a concurrent schedule. So again, we have some initial account values. A is 100, B is 200, and C is 300. And then here we get the balance in B, which is 200, right? So we write that into our balance variable here. And then before we finish this transaction T, we immediately going to execute the first operation of transaction U. Okay, so I'm executing now. Now this is a different variable balance. Okay, because this is a local variable that is only local to this transaction here. And this balance variable is local to this transaction. So again, I'm reading the balance of B, and it's still 200, right? It hasn't changed. And now I'm setting the balance of B by multiplying this with 1.1, and so it will become 220. Okay, and afterwards, I'm executing the second operation of transaction T. All right, so I'm also setting the balance now of B now by multiplying balance by 1.1, and this will now be 220. Okay, and this is probably not what we want, right? Because something has happened since the last time you read this balance from B. This is not exactly the same that we would get if we had just executed this transaction T by itself. And then we're withdrawing from A 1/10 of what is written in our balance. And since A has a starting value of 100 and balance is 20, so we're left with 80 on A. And then finally, we're withdrawing from C, again, 1/10 of our balance variable. And this will be, if C is initially 300, this will be 280. No, so it's the same database, right? that we're looking at is just two different processes. One is transaction T and the other one is transaction U. So the variables between these two are not shared. So these are local variables. All right. Okay. So let's look at some shortcut notation that we can use here and some more examples for schedules. So let's say we have two transactions T1 and T2, and we use the notation W1X and R1Y to say that transaction 1, that this is the operation of transaction 1, so that's why it's a 1 here, and it's a write operation to some item X, okay? And it doesn't really matter for us what we're writing to X, so we're not worried about that at this point. It only matters to us that it's a write, okay? And similarly, this is a read by transaction 1 of the item Y. Now down here, we have some operations for transaction T2. So we're reading from X, we're reading from Y, and then we're writing to Y. So what's a possible schedule for T1 and T2? Well, this would be a possible schedule, right? So first I have the first write for transaction 1 of X, then I'm reading in transaction 2, so this one here, of X, then I'm again executing the operation of transaction 1, so I'm reading Y, and so on. So this would be one possible schedule. Okay. Now, is the following one a serial schedule? What do you think? It's not. That's right. Why is it not a serial schedule? Well, because I'm simply, before this first transaction T1 here was done, right? So I started executing some of its operations, but then before I executed the last one, I already started with the second transaction. So it's not a serial schedule. Okay, but note that I did not change the order of these operations here. So I can never change the order of these operations here. So I can't, for example, now do this read here before this write. So that order has to always be fixed, but I might interleave these operations with each other. How about this schedule here? Is that a serial or concurrent schedule? That one's a serial one, right? And you can see that we're first executing all the operations of T1 and then all the operations of T2. So we already seen a bit that we need to be careful about executing transactions in a concurrent way. So there's some consistency problems that we may encounter. And the first one that I want to mention is the lost update problem. So that happens when there's a write conflict. Okay, so one transaction writes one item, and then another transaction writes the same item. So you have two transactions that access the same database item, and the operations are interleaved in a way such that the result becomes inconsistent. I'll show you an example for that on the next slide. A second consistency problem that we may encounter is the inconsistent retrieval problem. So this is not a write-write conflict, but a read-write conflict. So for example, transaction T1 might be calculating an aggregate summary function on a number of records. So this would, for example, this could be this total value that we calculate for all the branches that we just saw in the previous example, while other transactions are updating some of these records. Now, it can happen that the aggregate function may calculate some values before they are updated and others after they are updated. And of course, as a result, you might get some inconsistencies. So here's an example for the lost update problem. All right, so again, we have two transactions T and U. So we're reading from item B, we're writing this in balance, and then we are writing to B by adding 20 to balance, and then we're writing to A by subtracting 20 from balance. And similarly in transaction U, we're reading from B, and we're saving this in our variable balance, and then we're writing to account B by adding 30 to balance and to C by subtracting 30 from balance. And now down here we have a schedule. We start by executing the first operation of transaction T. Okay, and for these initial account values down here, the result will be 200. And then we perform some operations of transaction U. And we again are reading the current balance of B. So this would still be 200. And now we're writing, we're executing a second operation. So we're writing to B balance plus 30. So this is 230 now. Okay, and now we're jumping back to transaction T. We're executing this next operation. We're writing to B balance plus 20. Okay, so now we wrote the value of 220 to B. And you can already see that this doesn't really make sense, right? Because we only increased the balance of B, but somehow it's now less as it was here. Okay, so this update here, this one was lost. So this is a lost. So we have a right conflict between these two writes here. Okay. All right. So I already mentioned to you what a serial schedule is. So a schedule S is serial if for every transaction that shows up in the schedule, all the operations of that transaction are executed consecutively in the schedule. So there's no interleaving of operations of different transactions. And of course, if you have a serial schedule, you automatically get consistency. So there's no way for you to get an incorrect result. So there's a question in chat, how much once we change the variable, then we update to global. Not sure I understand the question here, but we'll talk more about these, how these things work, maybe afterwards. This will become clearer. Now, of course, the performance question comes to mind here, right? So serial schedules automatically give us consistency, but they're actually quite inefficient because interleaving of operations from different transactions isn't allowed when you have a serial schedule. And that can lead to low CPU utilization when a transaction waits for a disk input-output to complete while, or for another transaction to terminate, right? So this might slow down your system quite considerable. Now, a serializable schedule, on the other hand, is a concurrent schedule S, which is equivalent to a serial schedule. So it's not a serial schedule, but it's equivalent to one. Okay, and we'll talk about what we mean by equivalent in a second. And the nice thing about the serializable schedule is that it guarantees database consistency, and it may have better performance because it's concurrent. Okay, so it gives the benefits of concurrent executions without giving up any correctness. So in practice, it's quite difficult to test for the serializability of a schedule, but we'll talk more about that in a second. So let me first, I missed some questions here. So we're assuming that balance is a local variable there, okay? For each transaction, each transaction has its own copy of the balance variable. It's just some program variable. So here again, let's look at the two transactions that we saw 2 slides earlier, right? T and U. So where we increase the balance, and so basically we're having these 3 accounts, A, B, and C, and we are doing some increases and decreases here. And similarly for transaction U. All right, so this schedule here that we get, where we first execute these two operations from transaction T, then we do these two operations here from transaction U, and then we do this operation and then this one here. So is this equivalent to a serial schedule? What do you think? So what would be a serial schedule? How many serial schedules are there for these two transactions? 2, exactly, right? So either we first have T and then U, or we have U and then T. That's the only possibility. So meaning I'm executing all operations of T first and then all operations of U, or the other way around. That's the only way I can have a serial schedule. So is this schedule here equivalent to either of these? And equivalent means that the result from the schedule is equivalent to a serial schedule. So it is actually equivalent to this one here, right? To first executing T and then U. Okay, so this is an example of a serial equivalent schedule, and we'll come back to how to make this a bit more formal and to determine when a schedule is serial equivalent to a serial schedule. But first, let's look at the various conflicts that we can get when we have reads and writes. Okay, so if you have two transactions and both of them read the same item, can there be a conflict? No, right? Because it doesn't matter how you order these two operations, it makes no difference, right? So they both only read the same item, so there can't be any conflict. But if one of them reads and the other one writes, then that really depends on the order of the execution. So there can be a conflict. Similarly, if both of them write, there can be a conflict, right? Because we saw that this lost update problem on a few slides earlier when two transactions write the same item. Okay, so we might get an incorrect result in that case. So let's classify schedules depending on whether they're serializable. And to this end, we need to define what we mean by conflict equivalent schedules. So two schedules are called conflict equivalent if the order of any two conflicting operations, meaning a read-write or a write-write of the same item, is the same in both schedules. Okay, so we'll see some examples what we mean by that. But the definition is quite simple because I only need to look out for these conflicting operations. And now a schedule is conflict serializable if it is conflict equivalent, according to this definition up here, to some serial schedule. Okay, so let's look at some examples here. And maybe I can run a quick poll on that. And try to answer within the next 20 seconds, as we're a bit low on time. All right. 5 seconds more. Okay. And most of you are saying yes, and that is the correct answer, right? So these are conflict equivalent because you can see that the order of the conflicting operations is exactly the same in both schedules, right? So what are the conflicting operations here? Well, for example, the read of A and this write of A, that would be a conflicting operation. And that's the same order here. And similarly, this write here and this read and this write here and this write. So also this order is exactly the same, right? Okay, and this read B here doesn't matter because there is no access of item B in the second transaction. Okay, and now let's look at these schedules here. So we have 4 schedules of the same 2 transactions, T1 and T2. And up here we can see schedule A, which is a serial schedule. So it first executes T1 and then it executes T2. Similarly, schedule B is also a serial schedule. So it first executes T2 and then it executes T1. And C and D, on the other hand, are actually concurrent schedules. All right. So now let me run another poll. And try to finish in the next 20 seconds. So correctness means that it gives the correct result, right? So I don't get an inconsistent result here. Correctness means that it's equivalent to a serial schedule. So if there's a schedule that is not equivalent to a serial schedule, then it doesn't make sense, right? It's not correct. Okay, and let's end the poll. And most of you have gotten this right. So schedule C is actually not correct. But of course, schedules A and B are both correct because they're serial schedules. So that's not too surprising. But also schedule C gives the correct results, right? So if we have, let's say, if the initial state was X is 90 and Y is 90 and N is 3 and M equals 2, then if we execute T1 and T2, we would expect that X should be 89 and Y should be 93. Okay, because that's the meaning of these transactions when they're executed in serially, right? Okay, and that's also what we get if we execute schedule C. Schedule D. All right, but what's the problem in schedule C? Did anyone identify any problem with schedule C that comes to mind here? So we actually have the lost update problem here, right? Because you can see that we're reading something from X here in transaction T2, and then we're performing some computation on that. But here we're doing an update on X. Okay, but this update here is lost in transaction T1 because we're also updating it just later on without reading it again. Okay. Oh, yes, you're right. So yes, we're overwriting X. Yes, that's right. So which one is, yeah. Mm-hmm. Okay, so that's why schedule C is not correct because of this lost update problem. And now let's look at, how to make this easier to see when something is a correct schedule. So for that reason, we're going to define the serialization graph, which are abbreviated as SG. They're also called precedence graphs sometimes, and you can use these to test if a schedule is conflict serializable, meaning correct. So a serialization graph is a directed graph. So you have one node per transaction. And we add edges to our graph. So we add an edge from transaction Ti to Tj. If one of the following three conditions hold, meaning there's a write-read conflict, Ti executes a write of X for some item X before transaction Tj executes a read of X. And similarly, we do that for read-write conflicts and also for write-write conflicts. Okay. So we always draw a directed edge from the transaction that performs the first operation to the transaction that performs the second operation, assuming the two operations are conflicting. All right, and this is exactly the meaning of such a directed edge in the serialization graph. So the edges of the serialization graph effectively determine the execution order of transactions, and we'll see in a second what we mean by that. Now there's the theorem that says a schedule is serializable, meaning it's equivalent to some serial schedule, if and only if the serialization graph is acyclic, meaning it doesn't have any cycles. Okay, and I won't prove this here, but you can very easily convince yourself that this is true. But the nice thing about this theorem is that it allows us to say something, to devise a very simple test for serializability, right? Because we just need to check if the serialization graph is acyclic. And if it is, then we know that the schedule is serializable. Okay. So here we have two transactions, T and U. And we can see that we have this conflict here between, for this item I, right? So we're writing it here, and later on we have a read. So according to the rules of how we construct the serialization graph, we will have to draw an edge from T to U. Okay, so this would be the serialization graph that we get. And similarly, we can see that this read here of item J conflicts with this write here of item J laid down by transaction T. So therefore, we would also have to have an edge from U to T. And in some cases, we also like to add the name of the item that is the one that is conflicting here, all on top of the edges. Okay, and sometimes there's more than one item. All right, so in fact, yeah, okay. All right, so here we have the two top schedules from before, and let's draw the serialization graph for them. So that's very easy, right? Because these are serial schedules. So obviously the serialization graph will consist of two transactions, meaning two nodes, right? One for each transaction. And I can only have an edge from T1 to T2 because all the operations of T1 happen before the ones of T2. And let's see if there is a conflict. So I'm reading X here, and I can see that I'm writing X here. So there is an edge from T1 to T2, and I will label it using X. Okay, and similarly for this one here, we can see that it's the arrow is the other way, right? So again, I'm first reading here, and then I'm writing. So it's not that, so sometimes there's a question in the chat. So sometimes you might write something without reading. So this is just here for the examples, but it often makes sense to first read something. All right, and now here we have the two lower schedules, which are the more interesting ones, right? Because these were concurrent schedules. Okay, so let's see what we get here. Again, we have two transactions, T1 and T2. And now we have a read of X here. And do we have any following writes? Yes, we do. So we have an edge from T1 to T2 labeled X. And anything else? Any other items that show up here? No, we're reading item Y, but there's no access to Y. So that's fine. Now let's look at transaction T2. And we have a read of X here. And later on, we have a write here. So we have this directed edge here. And we also label it using X. And that's all there is. And you can actually see that we have a cycle in our serialization graph. And therefore, this is not serializable. Okay, so that's why this was not a correct schedule. And this is exactly, this matches our intuition from before. Now, let me show you this one too. Let's look at this schedule here. Okay, so we're reading X in transaction T1, and then later on we're writing X. So we have this edge labeled X. And anything else? No, not from T1. Okay, and from T2, we're reading X here and we're writing X, but you can see that we're not accessing X later on in T1. So there's no edge from T2 to T1. So this serialization graph does not have a cycle, and therefore it is serializable, and that's why this schedule was correct. Okay, and maybe the last thing for today is this more complicated schedule. Okay, so now I have 3 transactions. They're doing some various reads and writes, as you can see. And down here, I have a schedule for these transactions. So I now have 3 transactions. So we'll need to add 3 nodes to my graph, T1, T2, and T3. And now let's add the edges. Okay, so let's start at transaction T1. So I'm starting at the first operation. I'm checking this is a read. So are there any following writes? So there is a write here in transaction T2. So I need to add this edge here. Okay. And in transaction T3, there's no access of X, so that's fine. And here, okay, and here I'm accessing Y, but there's no further access of Y, so that's the only outgoing edge that I have for T1. Now let me find the outgoing edges for T2. So I'm starting up here, right? So I'm accessing Z, and here I'm reading Z, and here I'm writing Z. So I will have an edge from T2 to T3, labeled Z. I'm reading Y, and later on in, why is it zooming in? Later on, I'm writing Y, so I will also label this with Y. Okay, and again, that's everything because here there's no access to X. And finally, I'm looking at transaction T3, so I'm accessing Y here, a read of Y, but here there's a write of Y, so I need to have this arrow here. T1 to T3. Okay, maybe I made a mistake here. Let me just check. T2. So I'm not sure I understand your question, but maybe let me just finish this because we're already quite out of time. Oh, you may mean that I forgot something here. Yeah, you're right. So T2, so we're accessing Y here, right? And in transaction 1, we're also accessing Y with a write. So obviously there is a conflict between these two. All right. Okay, and I think now we have all the edges. So you can see that this can become more complicated. And is this schedule therefore correct? Is it serializable? That's the last thing I'm asking for today. It's not, right? Because we have actually multiple cycles here, right? So we have one cycle here, we have one cycle here. So it's not serializable. Okay. All right. Any more questions? What do you mean not only look at one variable? So we need to look at all the operations, right? So for each operation that accesses any item, I need to check whether there's any conflict in the subsequent operations that show up in the schedule. And if there is, then I need to add an edge for that. But of course, there's only a conflict if the operation is accessing the same item, okay? Okay, go back to slide 23. You mean why can we read a balance of 220? Oh, so okay, so there are two things happening here, right? So we're not yet assuming that all these properties, that these asset properties already hold, right? So they're not guaranteed in all these schedules, okay? So we would like these assets properties to hold, but they might not hold. Yes, so B is a globally, B is an item in your database. And let me go back to the last slide because there was another question there. So where's that question? No, from T1 to T2. Oh, you mean here? So why would there be, you're saying that there should be a Y on this edge? Or from here to here? Yeah, we have a Y, right? On the edge from T2 to T1, we added the Y. Oh, no. So, okay, so maybe the last point that I would like to make here is that, it doesn't matter exactly what the items are here. Okay, so as soon as you have a cycle, you have a cycle. It doesn't matter what labels we have. Because the point is we can't find an equivalent serial transaction if there's a cycle. That's right. So it doesn't matter. So these labels are just for us, right? But for testing whether it's serializable, you just need to check for cycles. That's right. So we don't care about the variables. That's right. Yes. Okay, great. Then I'll, yeah. Mm-hmm. Okay, then let me close the lecture for today, and I'll see you next week. Actually, next week is a break, if I'm not mistaken, so I'll see you in 2 weeks. All right. Yeah. Yeah, today's lecture was not about April Fool's Day. So all the things that I told you are still correct. So yeah, I'll see you in 2 weeks.